All right, good morning and welcome back to microprocessor course. So in today's class, we're going to continue with cache memory. We're going to talk about cache memory performance models. Then we talk about some design options for improving the cache memory performance. Then after that, we're going to have to introduce some other internal memory, including the synchronous DRAM and the DDR DRAM. But before I start today's class, I'm going to check on your attendance. Class 5, number 1, 2, 3, 4, 5, 6. Class 5, number 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 17, 18, 19, 20, 20, 21, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 30, 30, Peter. 6, number 1, number 2, number 5, 6, 5, 6, 6, 7, 8, 10, 11, 12, 13, 14, 15, 16, 17, 20, 21, 22, 23, 24, 25, 26, 26. 626. 27, 28, 29, 29, 629. Hurry. 630, P21, 615. Good. Now, as I said, we're going to finish up the cache memory. Then we talk about other internal memory. So if you still remember, we talked about the cache memory, and you know that the cache memory is placed between the central processing unit and the main memory to avoid multiple accesses of the central processing unit to the main memory, because the main memory is slower if you compare to the cache memory. And because the cache memory is smaller than the main memory, not all the blocks from the main memory can be loaded at one time into the cache memory. We talked about cache mapping techniques. Main memory. Here, the way from the central processing unit to the cache memory is faster if you compare to the way of the main memory to the cache memory. This is slower. Now, we talked about the cache performance model last class. We're going to finish up this section of cache memory. We have to talk about the cache timing analysis using different equations for different cache memory mapping techniques. But we needed to have a look at the following key concepts that we're going to use to discuss about the cache performance model. We have the time that the system spends on comparing the address tag from the central processing unit and the cache line is tag. Then that is the CTT. Then we have the time that the system spent on reading the cache line. The cache line needs to be read to retrieve the data if there is a match with the tags. Then we have the time that the system will spend on transmitting the data to the processor. It might be a byte or a word. So we need this time for the system to transmit the data to the central processing unit. So we needed to calculate how long does it take the system to retrieve the data when it is in the cache memory. Or if it's not present in the cache memory, on a cache miss, what is the time does the system spend on retrieving the data when it's not in the cache memory? It all depends on the cache memory mapping techniques. We talked about direct mapped cache access. Now, you know, because we have many blocks into the main memory, and they can't be loaded into the cache memory at the same time, we need the cache memory mapping techniques. We discussed about direct map. For direct map, if you still remember, we have to find the cache line for each block from the main memory. The cache line is equals to the block number mod what? Don't still remember? How do we found a cache line for a block from the main memory using direct map caching technique? The cache line is found using the following expression. The block number mod number of lines. You don't still remember? Number of cache lines. Then for direct map, we have the address from the central processing unit, which include the following field. We have here tag for addressing purpose. Then we have the line number needed to be given into the address from the central processing unit. Then here we have line number. After the line number, we need the offset. The offset does help to select a byte or a word within a block. So we have the offset here. Now, the system needed to check the tag field against the line is tag. Then, if the data is in the cache memory, it needs to be returned to the central processing unit. So we need to calculate the heat time. How long does it take the system to return the data if it is in the cache memory? Now, if there is a miss, the system needed to expand its data request to the next level into the memory hierarchy. So we needed to calculate the heat time for direct map. Heat time for direct map T heat equals to the time that the system spent on reading the data plus the time that the system spent on transmitting the data to the processor, plus the time that the system spent on comparing the tags. That is the tag from the central processing unit, and the cache memory is tag. So here we have the heat time for direct map caching technique. If the data is not available into the cache memory, we need to calculate the time for a miss, which is equals to the time that the system will spend on reading the data plus the time that the system spend on comparing the tags, the TCT. So here we can calculate easily the time for hit and the time for a miss for direct map access memory. Now we have the direct map with speculation. Why direct map with speculation? Because it allows a simple, faster data recovery to the central processing unit. Now, because in the address that is provided into this address from the central processing unit, we have the tag and the line number. That means that once the address is computed, once the address is known, there is a possibility that the cache line is also known. So here we have the line number. That means the processor is able to use the data before confirming that there is a match between this tag and the cache memory is tag. So in other words, we have the checking and the fetching that are being done at the same time for direct map with speculation. For direct map with speculation, we have direct map with speculation. We have the hit time, which is equal to the time that the system spent on reading the data, plus the time that the system spent on transmitting the data. Now, you see that the time that the system spent on comparing the tags for direct map with speculation is equal to 0 because the fetching and the checking are being done at the same time. So the time for comparing the tag is not being taken into consideration here for direct map with speculation because we have the checking and the fetching that are being done at the same time. That's why here for the time that the system spent on hit, it does not include the time that the system used to compare the tags. The miss time, there is no change for the miss time. We have the miss time, which is equals to the time that the system spent on reading the data plus the time that the system spent on comparing the tags. Now, the next one is the fully associative. For fully associative, tell me, for fully associative, well does a block from the main memory loaded into in which cache line? Fully associative. Hello? A block from the main memory using the fully associative can be loaded into which cache line? In which cache line? Huh? Are you there? Which cache line do we need to load a block from the main memory? We talked about this last class. Should be aware about this. So in which cache line does a block from the main memory need to be loaded into? Huh? A block from the main memory can be loaded into any cache line. Block from main memory can be loaded into any cache line. Thus, for the address from the central processing unit, for fully associative, it does only include the tag for addressing purpose and the offset. It does not include the line number. That means that the line number is unknown until the tag comparison is done, because the address from the central processing unit does not provide any information related to the line number. That's why here we say that the line number for fully associative cache is not known until the tag comparison is done. Then, if there is a hit, we have the hit time that match the hit time of the direct map cache. So we have the TR, the time that the system spent on reading the data, plus the time that the system spent on comparing the tags, plus the time that the system spent on transmitting the data. So for the miss time, it only depends on the tag comparison. It only depends on the tag comparison. It does not include the time for comparing the tags. So for the hit time, fully associative hit time, we have the time that the system spent on reading the data plus the time that the system spent on transmitting the data plus the time that the system spent on comparing tags. For T-miss, the miss time, we have the time that the system spent on comparing tags. Then the third one is set associative. Set associative. Now, for set associative, a block from the main memory can be loaded in which cache line? Set associative. In which cache line does a block from the main memory load into? Cache line. Here, or set number. In which cache line? Hello? Tell me. We talked about this last class. In which cache line does a block from the main memory need to be loaded while using the set associative? In which cache line? In which cache line? How do we found the cache line? For set associative, we know that the cache memory is divided into different sets. Then within a set, we have many lines. So to found a cache line for a specific block from the main memory, we get we needed to use the following expression. We need the block number mod number of sets. Then the address from the central processing unit include the following field. It does include the following field. It includes the tag. After the tag, we have what? We have not line number, but the set number. We have the set number here. Then we have the offset field. The offset field, which can help us to select a byte or a word within a specific block. So this is how we can found a set for a set associative cache. Now, for set associative cache, data cannot be transmitted until the comparison of the tag is done, like we have seen for the direct map caching. So we have a circuitry which allows loading data blocks from all the lines in a set. So that means there is no way for the set associative to do the fetching and the checking at the same time. So data is transmitted only after the tag check is done. Now, the timing equation for the set associative is as follows. We have the time for hit, which is equals to the time that the system spent on reading the data plus the time that the system spent on transmitting the data plus 1 minus fp times the time that the system spent on comparing the tags. where fp is the fraction of the time that the way prediction succeeds. Then we have fp equals to 1. If we have fp, if fp equals to 1, fp equals to 1, we have the heat time, the time for heat, which is equals to the time that the system spent on reading the data plus the time that the system spent on the transmitting the data, which is what? Which is the heat time for direct map with speculation. So if we have the fp equals to 1, that means we have the heat time for the set associative, which is equals to the heat time for direct map with speculation. We have the T miss, the time for miss, which is equals to the time that the system spent on reading the data plus the time that the system spent on comparing the data. So this for the set associative cache model performance. Now, if we have the fp equals to 1, that means it behaves like the direct map cache with speculation, and this is the best scenario. If we have fp equals to 0, that means we have a set associative cache without any prediction, and this is the worst scenario. Now, here we have a table which is summarizes all these cache performance models that we just talked. We have the direct map, we have the heat time, we have the miss time. We have direct map with speculation, time for heat, and time for miss. Then fully associative, set associative, and set associative with way predictions. Now, we needed to have a look at some design option on how improving the cache memory performance. We have to calculate the average time to access the data in a memory hierarchy, which is equals to our probability of taking a path and times how long does it take to retrieve the data if it is in the path. Or it is also equals to all probabilities in the path times all the time in the path. It is equals to the summation from I equals to 1 to n, 1 minus hg, which is the heat time, times the h1, which is the heat time for the level 1 cache memory, times the heat time for level 1 memory. And n is the number of levels in the memory hierarchy, and the Ti is the total time that needed by the system to access the data in level Mi cache. So we talked about this arrangement to show the contribution of the level 1 memory explicitly. So we have the average access time, which is equals to the time that the system spent on retrieving the data when it is available into the level 1 memory, that is h1 times t1 plus 1 minus h1 times the t penalty. The t penalty. Here, the t penalty is the minimum time, is the average time that the system spends on accessing the data if it is not available into the level 1 memory. So T1 here, it is equivalent to the heat time for the level M1 memory. Now, what are some improvement techniques that can be used for the cache memory? So we can have way prediction. We can have a way prediction. That means we have set associative that needed to lower the heat time. So since we have a way prediction for the cache memory, this has to provides some advantages of having lower heat time. When it comes to the cache size, we needed to discuss about the cache size. If we have a smaller cache size, that means that we have a faster heat time. As you know from the memory hierarchy, with a small size of the memory, the time to retrieve the data, the time to return the data from the memory is going to be less. So with a smaller cache memory, we have a faster heat time, but with the smaller cache memory, we're going to have a higher mislay, but with the larger memory cache size, we have the lower mislay, because we have enough space to have the most recently used data. So now, when it comes to the cache size, understand that the smaller cache size allows the system to return the data within less time. That means it has a faster heat time, but for larger cache memory, it has to lower the mislay. Now, we needed to talk about the line size. The line size. We have a cache memory which includes enough cache lines. We have the cache memory. This is the cache memory. We just talked about the whole size of the cache memory. We just talked about the whole size of the cache memory. Now, if we have a smaller cache memory, we have faster heat, and if we have a very big cache memory, we have lower mislay. So how about the line size? The line size here, with a large line size, this can reduce the miss rate, especially if the spatial locality is used. This may increase also unused fetch. So it has larger line size. It has the advantages of reducing the miss rate if the spatial locality is being used, but as one of the drawbacks, it may increase unused fetch time. Now, with the cache associativity, we needed to talk about the different associativity that we have learned. So let's say we have a direct map with speculation. That means we have a direct map with speculation. The fetching and the checking are being done at the same time. So that means it has a lowest heat time, because the system does the fetching and the checking at the same time. This has a significant, it has a positive impact on the heat time. We have a lowest heat time. Now, for fully associative, we know that a block from the main memory can be loaded into any cache line. That means we have advantages of having a highest heat time. So now, here we have higher associativity. Now, with direct map cache technique, we know that a block from the main memory needed to be loaded into a specific cache line by taking the block number mod, the number of cache line. Then we need to have multiple blocks from the cache memory competing for the same cache line. So we have higher conflict miss. But if we have a higher associativity, this has to lower the conflict misses that are being observed for the direct map caching technique. Now, with the instruction, if we split into the cache memory into instruction and data, we have level 1 instruction. We have level 1 cache instruction, level 1 cache data, or level 2 cache instruction, level 2 cache data. This has a significant impact on lowering the hit time because we have unified cache, which has also to lower the overall mislaid. So it is very important to note that into the recent technology of the cache, we have the cache which is split into data and instruction. So we have level 1 cache instruction, level 1 cache data. We have level 2 instruction, level 2 data. This will allow the system to have a smaller hit time. For prefetching technique, we need to reduce the hit time. It is very important that with the prefetching time, it does reduce the hit time. It does reduce the time that the system spends on returning the data if it is in the first level of the memory hierarchy. Now, the next cache performance improvement technique that we need to talk about is the write policy. The write policy. Write policy. We have learned the cache write policies, write through, which allows the cache memory and the main memory to be updated at the same time, for the same copy of the data. That means the cache memory and the main memory, they are always updated. One of the drawbacks of this write-through is that it has a higher memory traffic, which may cause some bottleneck problems. So to solve this issue, we had to discuss about the write-back, which only updates the cache memory, and the main memory will be updated when the cache line is about to be replaced. So for the write back, there is higher probability of the data loss because only the cache memory is updated, and the main memory will be updated later. That means the write back has a higher probability of the data loss if you compare with the write through. Now we have to discuss write through as one of the improvement techniques for the cache performance. We have the write through with write allocated, which has a significant impact on lowering the mislaid. Now we have the write through without no write allocate. It has to lower the penalty time. Now, for critical word first, this is very important that the word that is requested needs to be returned first. So this reduces the penalty time as well because the system is sending the requested word first. So these are some of the cache performance techniques that we needed to discuss. We have the way prediction that lower the hit time. We have the cache size. Small cache size has to provide the advantage of having faster hit time. For big cache size, it has to lower the miss rate. When it comes to the line size, these reduce the miss rate, especially when the spatial locality is being used. Then we have one of the drawbacks of having a larger line size. This may increase unused fetch time. When it comes to the cache associativity, we have the direct map with speculation. Since the fetching and the matching are being done at the same time, this has to lower the hit time. Then we have the fully associative, which has a significant impact on the hit time. That means we have highest hit time. For higher associativity, it has to lower conflict miss, which is being observed while using the direct map because a block from the main memory needed to be loaded into a specific cache line. That means more than one blocks from the main memory are competing for the same cache line, then these we have with higher or associativity, lower the conflict miss. So if you split the instruction and the data caches, let's say we have level 1 cache and for instruction and the level 1 cache for data, this has impact on having smaller hit time because we have unified cache which lower the overall miss rate. So with a prefetching technique, it reduces the hit time. Write policy with allocate, we have to lower the miss rate. And with the word fast, critical word fast, it reduces the miss penalty because the request, the word is returned in a few is returned the fast. Now, here is the cache performance improvement technique summary. We have discussed all these techniques: way prediction, cache capacity, line size, degree of associativity, and the more flexibility with replacement policy. Cache unity, we spent the cache memory into instruction or data cache, or we have the prefetching technique, the write through, critical word fast, victim cache, and write passes. So this is a summary of the cache performance improvement techniques, and it is the end of lecture number 15. Any question related to this lecture? Any question related to this lecture? Lecture number 15, when we talked about the cache memory, logical organization of the cache memory mapping techniques, right policies of the cache memory, design option for improvement for the cache memory performance, cache performance improvement techniques. Any questions? All right, so since there is no questions, we're going to continue with lecture number 16. Lecture number 16. Now, for lecture number 16, we're going to continue with internal memory. We're going to have a short review for the cache memory because cache memory is one of the internal memory systems. Now, what do you call internal memory? The internal memory is based on the location of the memory. Internal memory include registers, cache memory, and main memory. So this, we call them internal memory based on their location. Where are they situated in the computer system? They are internal memory. So we're going to talk about internal memory. We're going to talk about especially synchronous DRAM and the double data rate DRAM. So it's just a kind of introduction to this type of memory. We're going to go through in more details in advanced microprocessors. Now, we have the memory hierarchy. The memory hierarchy, we have the registers. We have different levels of the cache memory. Then we have the main memory. Then we have the secondary storage memory. In this memory hierarchy, now understand that registers and these different levels of the cache memory and the main memory, we call them internal memory system because of their location into the memory, into the computer system. Now here we have the registers, different levels of cache, and the main memory as the internal memory. Now, why the cache memory? We talked about this. It has to be designed to combine the memory access time of expensive and high-speed memory and the large memory system of the less expensive, lower-speed memory. Here we have the computer system which include only a single cache memory. This away from the central processing unit and the cache memory is fast, and the unit of data transfer is a wait Here, the way from the cache memory to the main memory is slow, and it has a block of data as a unit of the transfer. The picture B depicts the computer system with different levels of cache memory, and we have 3 different levels of cache. Level 1 is faster than level 2, and level 2 cache memory is bigger than level 1 memory and is slower. And the level 3 is bigger than level 2 memory and is slower if you compare with the level 2 memory. Then we have the main memory here. So all this main memory, we are missing here registers, different levels of cache memory, and the main memory, they are all internal memory. We talked about the cache mapping technique, direct mapping. Each main memory block needed to be mapped into only one possible cache line. Here is the mapping expression. We have J modulo M, where J is the main memory block number. Then we use the modulo. Then M is the total number of cache lines. For fully associative, we have a block from the main memory that can be loaded into any cache line. For set associative, the address needs to be split into the tag and the set number. We need to know what is the set number in which the block from the main memory needs to be loaded into. And here we have the index, which immediately addresses the set in the cache, in which set has the block from the main memory needs to be loaded into. Then each set has multiple places, has multiple lines. That means if a block from the main memory needs to be loaded into a specific set, the block has many options to be loaded into any line into a specific cache set. Now, a short introduction on the internal memory, including the synchronous DRAM and the DDR. We have the main memory interface, which is a major bottleneck in higher performance processors. Why? This is the most critical pathway in the computer system. We have seen that the way from the cache memory to the main memory is slower if you compare the path with the central processing unit and the cache memory. So we have the DRAM memory, which is the fundamental building block of the main memory. Now, it has been used in the computer system setting in 1970s, and it has the following limitation. Now, traditional DRAMs, they are limited with internal chip architecture, and another limitation for them is the interfaces to the processor, its memory bus system, which is very slow. Now, to solve the issue of the traditional DRAM, we needed to think about adding a static RAM between the central processing unit and the main memory. But how about the cost? Because we need also to have the computer system at affordable price. So this is not the right option because the static RAM are expensive. Then we need to increase the cache size, but this will have a negative impact on the computer performance. So recent improvements needed to be focused on the DRAM itself, not adding SRAM between the central processing unit and the main memory. So needed to talk about the key improvement in the DRAM technology. We have the synchronous DRAM and we have the double data late DRAM. Now here is the synchronous DRAM. The synchronous DRAM is widely used in modern computer system, in modern DRAM types. And unlike the traditional DRAM, we have the synchronous DRAM, which is synchronous. That means that we have data which is being coordinated with an external clock signal. So this is your 5-minute break. Take your break, then we're going to resume class after break.